Thanks very much. I appreciate the invitation to speak here. And I will, I've got about the amount of material for time plus questions, but if there's something you don't understand, please interrupt. Otherwise, I'll zoom through. If I have an opportunity, I'll come back to this, but since this is up on the screen right now, this is a real-time map of the winds in our region right now. So faster moving particles is where the wind's blowing more. I'll show you some maps that are 1 year averaged, but what that misses, and this display captures, is that the high winds are in different places at different times. So if I were placing wind farms right now, I'd put a swath of them along here. I'd certainly have some right here, maybe some offshore. And 2 hours from now, you'll see different locations. So part of what's variable about the wind is that it blows more or less in different locations at different times. And we can't move our wind farms around in any economically feasible way. So we'll come back to this. This will be a central part. So more conventional PowerPoint-looking display here with title and such. So variable generation. And what's the problem I'm working on? The first bullet there is the problem. I've given many talks where that's 8 or 10 slides instead of one bullet. If you want the 8-slide version, see Michael Oppenheimer. He's got a very expanded version, but I think you know what I'm talking about there. And the second bullet is a very rough number, but we want to do something like 80% reduction in anthropogenic additions to CO2 in the atmosphere. Non-trivial because major economic activities, as well as many academic ones, emit CO2, and you can make an ordered list. You know, it's not just everything we do is equally important, but electric generation is 39% and transportation is 32% of the anthropogenic CO2 emissions. So although we want to deal with other things, industrial non-electricity use, building heat, those are good to work on too. But if we can deal with a lot of the problem of these two, we're dealing with 70% of the anthropogenic CO2 emissions. So that means we want to focus. We don't want to forget those two. Maybe somebody else is working on those two, but somebody's got to be working on those, and I'm one person who's working on those. So then rephrasing that first bullet problem, it gets transformed into perhaps a more manageable problem, which is we want to produce electricity from non-carbon sources and use it for transportation as well. Of course, there are other solutions to the problem, re-sequestering the carbon and so forth. But this is the way I'm framing the problem and sort of defines what I'm working on. So background, where I'm coming from, I'll take a question on that if there's any. But I won't take a question on whether humans contribute to climate change. That's somebody else's department. I'm already convinced on that one. Okay, no questions here. Okay, so just, apologies to most of you who know plenty about this already, but when we talk about the electric system, we're talking about generation. That is the production of electricity, either from other fuel sources or moving fluids or whatever. Transmission, and that's also called the grid. And transmission generally refers to high voltage above 30,000 or so volts. There's also the distribution system. I'll just label that all with transmission. We're moving electricity from one place to the other. And then load jargon, industry jargon is load. That means when you're running appliances and turning on lights and so forth. So that's the electric system from end to end, not counting where the fuel is coming from and how people manufacture things. I will talk about power and energy, and everybody says, yawn, I know what that is. And okay, power, generally kilowatts, megawatts, gigawatts. It's a flow. And energy usually is kilowatt hours. That is, it's power over time. And I'm getting the very bottom cut off here. I don't know if there's an AV person who knows how to give us another line, but if not, I'll just read it. Energy is power over time. It's generally a unit like kilowatt hours, but I'm going to often refer to energy as average power. So you're going to see me talking about PJM, for example. The energy that it manages is about 70 gigawatts average. rather than gigawatt hours per year. It just makes it easier to compare power and energy if you put it in those units. And I will subscript with the letter A, which you would be able to see if the screen went down a little bit further. Okay, so for low carbon sources today, we're looking at most renewables, nuclear, hydro, the main ones. And since I'm trying to get 80% reductions, which is pretty challenging, I'm going to concentrate on the big stuff, which I think is solar, wind, and thermal gradients. And people would disagree on that. But to me, the big low-carbon resources are those three. Thermal gradients we don't really have technology for. So if I then take the next cut down, what's commercial today? I would say that's wind and solar. Some would add nuclear fission to that list, or perhaps other things. But the big industries rolling out gigawatts per year, sort of near market prices, that's, I think, wind and solar. Okay, so variable generation, I'm going to use that to refer to both wind and solar, and there's a few other low carbon sources that are variable generation. Now, every generator is variable generation, but thermal units, fossil fuel, and nuclear units are variable in the sense that they have unscheduled downtime. So it goes from full to zero very quickly. But these types of variable generation, solar and wind in particular, are changing constantly through the day. So this is a problem if you want to keep the lights on. So by variable generation, I mean electricity sources that vary with natural forces. These types of generation, variable generation, if you want to do a lot of it, if you want to do a wind turbine in the backyard, who cares? But if you want to do a lot of it, we've got three questions we have to answer if we're really going to make major displacement of carbon from generation. How much resource is there? And there are a lot of things I didn't put on my list on that slide, that first slide about low carbon sources, because they're too small. So you've gotten a partially pre-processed list here. But there's got to be enough resource to really do something significant. What's significant? Is it a quarter or half? But it can't be 1%. That's not worth, I mean, we've all only got so much time to study things and advocate and whatever we do. So we want things that are fairly large. Second, can we get steady power from variable generation? And maybe if we can't, we're not going to do any variable generation. There's 4 well-known climatologists who say you can't do that. So therefore you need nuclear power. That's the only way to deal with climate change. So, you know, that's an argument, but I'm going to try to do a little more analysis on how you manage variable generation than what I usually hear from those guys. And then the last cutoff bullet is a very important one, although I'd kind of like to cut it off sometimes, and that is how much will it cost? So 3 questions that we're going to return to. Is there enough resource? Can you get reliable power from variable generation? And what is the cost? Okay. Now, if you want other questions answered, maybe this is not the right talk for you, but these are the ones I'm going to try to answer. Okay, so how much resource? And I'll go through this fairly quickly. It's an easy one. This is a map of the wind power resources of the United States. And again, this is a year-long average. So we don't see all this variability hour by hour and day by day. We have an incredible resource for wind energy in the Great Plains. Central time zone, roughly, is what that is. So I think I first heard Bob Williams cite this figure that there's 2 or 3 states there that would produce enough electricity, if fully built out, for the entire country. So this is a very large resource. But it's not so close to the load centers, which tend to be more on the coasts. I mean, we've got Denver and Chicago and so forth. But there's a lot of resource there. Okay, let's look at another resource, which is concentrating solar. I just said solar, but we've got photovoltaic, solid-state conversion of sunlight into electricity, and we also have thermal conversions where you boil water or heat up sodium or whatever your favorite material is, and then you boil water and, you know, it looks like a fossil plant from that point forward. So that's really concentrated also. It's not spread out. Now, maybe if this is the thing to do, maybe we build a lot of transmission, but the United States has a large concentrating solar resource. Another interesting one in geographical distribution is rooftop photovoltaic. Okay, so where's the rooftop photovoltaic? That's a weird little patchwork. It's the rooftop photovoltaic resource is where you have good sunlight and roofs. So states that have more built infrastructure, buildings, have more rooftop solar resource, times the amount of sunlight hitting. So Florida's got sun and buildings. New York's got lots of buildings. It makes up for the lower incident sunlight. So what do these add up to? Maps are great, but we still need to get 80%. Is this 1% or 100%? So we're trying to make it for the United States. If you want to run the United States on these sources, you want 450 gigawatts on average. Sometimes you need more, sometimes less. But on average, you need 450 gigawatts, 450,000 megawatts, 450 million kilowatts, or 450 billion 100-watt light bulbs. Or is that right, 100? I think I'm off by an order of magnitude there. But so how much have we got in these resources? So wind inland, like you saw that big swath in the central time zone, 4,400, that's not a typo. It's about 10 times the resource needed to run the entire country electric system. These are from NREL references at the bottom of the page there, but this is a technical potential, so you drop it in half or a quarter to say what would be practical to extract. But this is a huge resource. Okay, offshore wind, about 2,000 gigawatts, about 4 times what we need to run the whole country. Rooftop solar, 93. And so that's going to be helpful, but it's not going to get us that 80% reduction. And then concentrating solar, you saw in the southwest there, 13,000 gigawatts, 13 terawatts. Now we have, we got to talk about cost and these other things, but we get to check the first item. Renewable energy, variable generation is not going to mean we have to live Spartan existences with very little electricity. It's going to mean we're going to have way more electricity than we need, at least now. Maybe we'll figure out ways to use all that electricity. But this is going to increase the electricity available to consumers in the United States, and the same is true worldwide, most regions at least. So that's looking at the US. I mean, I could do a world thing also. My colleagues Archer and Jacobson have done some very nice stuff on total resource worldwide. But I want to narrow instead because I'm going to have to understand variability, and that's more of a regional thing. So I want to look at a regional transmission organization. These are the often nonprofits, typically nonprofits, which manage the generation and transmission of electricity. RTOs. In Europe, they're called TSO, transmission system operators. The old term in the US was independent system operators, so it's a real alphabet soup. But these, we analyzed in the study I'm going to delve into in a minute, we analyzed PJM Interconnection, which is the people that manage the electrons that are running the lights in here and the projector and so forth. They're sort of North Carolina to New York, northern New Jersey, and then out to Chicago. I'll show you a map in a minute. So I want to look at some regional claims, and then we'll do a regional analysis. So this is the second bullet. We're trying to figure out if we do an X or a check by it, how much variable generation can be integrated? Can we keep the lights on? So there's lots of claims about this. It's kind of fun to review. Some are political, and some are actually studies. Here's a couple of political ones just for fun. Very high wind penetrations are not achievable in practice, pretty definitive. A practical upper limit for wind penetration is 10%. 20% would be the extreme upper limit. So it turns out this is not a peer-reviewed publication, And I'll let you make inferences about the politics based on the name being the Reason Foundation. The second bullet here is from the American Wind Energy Association. And they have been a long-term advocate for getting 20% of electricity from wind. So you've got this renewable energy organization saying the same thing as a shill sort of think tank, that 20% is a plausible upper limit for how much wind power in particular you can put on the system. So is that the right number? Let's look at a couple of studies. This is Denholm et al. In this study, they took a large wind farm in the Great Plains, and they said, let's try and make this into a baseload power plant. That is, get steady power out of it all the time. So they took a fluctuating variable generation power plant, a wind farm, and they added storage. And what they're doing is, and you can see from the colors, the color key there, the wind farm output, which is just straight onto the grid, is the purple or blue color there. The stored wind energy, when it goes over this nominal level, they've said we want to run at 900 megawatts, even though we've got a 1900 megawatt wind farm. Excuse me, they said over that, we're not going to put it onto the grid, we're going to put it into storage. This is actually compressed air energy storage, although it doesn't matter what kind of storage it is, the principle is the same. Excuse me. So at some point you fill up the storage. So you're blasting out almost full power from the wind for a day or so, and you fill storage. So then this green is just spilled. That is, you could be generating electricity, but you can't because you have no more room in storage, and you've said you're not going to put more than 900 megawatts on the grid. Now, later, the wind dies off, and you want to keep your 900 amount because you've got a contract, you get paid more if you keep it steady. So the yellow is discharging from your storage and putting it on the grid. So we did pretty well, you know, for whatever, day 2 to day 10, we were actually running at that steady 900 megawatts, making a base load power plant. But then we had a long enough time with little enough wind that the storage was exhausted. And now we go to zero. We fall off the edge of our storage cliff, and we're no longer providing the power that we said we would do contractually. There's a little bit of wind, just barely enough to put a tiny bit in storage, which is quickly exhausted. Now we're a fluctuating resource, and then at some point the wind blasts in again, and we're back to 900 megawatts. So this is the sort of first cut idea of how you make wind a steady resource. You take one location, and you add storage to that one location. Now, a different perspective is from, oops, I think I forgot something on the last slide. Yeah, right. So in this case, you know, you got enough power about 70% of the time. It's expensive because you bought a big storage resource just for this one wind farm. Okay, so here's another perspective. This is Hart this is DeLucchi and Jacobson. California study, and you can see from the key the different resources they were looking at. This is one example day, and here they had hydroelectric. Hydroelectric you can turn on and off. It produces no carbon, but you have a great deal of control over it. You can't put energy into it, but you can take it out. So early in the morning, in this case, we had a little bit of wind. And so not enough to really do anything. We had no solar. It's nighttime. This is a 24-hour scale on the bottom with noon in the middle. So the hydro is supporting almost all the load. And then as the sun came up, we start getting solar. And there's a solar thermal unit also in this mix. And photovoltaic, rooftop photovoltaic is the main resource here, and then the wind actually comes up quite strongly after. Hi.
Can I try to
sure.
Save the bottom of your
screen? Yeah. So if you can remember that graph, the argument here was we're going to take certain amounts of each of these, which is just sort of a priori picked, and they said, will this work? and they found, running it for 1 year on California, that that set of resources did work. It's probably hard to, I'm going to keep going even though I know it's probably hard to not concentrate on the video adjustments. So what we learned from that study is you can get a diversity of variable generation, and hydro is not variable generation except in very long time periods with droughts and stuff. So what we learned from that is that you can make a diverse set of resources meet load for a long period of time, a year. But we don't know if that's the optimum mix. And California is kind of an easy case because they've got a lot of geothermal, they've got a lot of hydro. Thank you very much, Dan. So this works, you know, and you can look up the article and all that. But is this the right mix, and does it apply anywhere else other than California, which has all these carbon-free resources? Okay, so PJM's a little bit harder case. There's not much hydro in this region. So there is a PJM study. It only went up to 30%, but at least we know from modeling what PJM thinks they can do. And they looked at PJM within the entire Eastern Interconnect. That's that cryptic EI abbreviation. Eastern Interconnect is sort of Eastern Canada all the way down to Florida. And the question for this study was, can you do 20% and can you do 30% wind by 2026? So they did hourly simulation. They also looked at some challenging days, broke it down to 5 minutes. And they just, again, picked, you know, they just said, well, we'll try, you know, 10% inland wind and 10% offshore wind. There's no systematic kind of decision of how much of what to have, but they had 6 different combinations, so that's great. And what they found was, well, they can keep the lights on. There's occasional reserve shortfalls, but in the 1-year model, they never had unserved load, which is utility jargon for the lights went off when you didn't expect them to. And overall cost of electricity is less than today, which is kind of fun. So, you know, wind's getting pretty cheap these days in windy areas. And what they found was that by putting 20 or 30% of wind on the system, they were displacing fossil at times that the prices were high. And because of, excuse me if I speak to the those who are familiar with power bidding for a minute, because it's a merit order effect on the bids, wind displaced the highest price, so that lowered the price all the way down the merit order. So there's this kind of amplifying effect when you put on a must-run or free-to-run resource like wind. And they actually reduced the cost of electricity with a moderately high, by kind of Reason Foundation standards at least, a moderately high amount of wind power. It's a model. They didn't actually do it, but they're on the way. Okay, so that's one way of looking at it. Look at studies, you know, look at sort of political statements, and then you can also look at national goals, because countries have, not the US so much, we've got the DOE has said there's a 20% goal or by 2030, so they're going to be a little slower than PJM thinks they're going to be. Germans want to get 80% of power from renewables. So these are by 2050. So these are political goals. You could say, well, you know, does it really mean anything, or is it just talk? I mean, that's a legitimate question. Denmark has a goal of 50% of electricity by wind power from 2020. It's coming up, you know, it's pretty soon. Yeah. Maybe, my number's 32, but 40 may be this week, I don't know. Yeah, it's close to that. And they're moving fast. Yes, right. So I said 32, and I don't claim that that's necessarily up to date. That could be 6 months old. And then Scotland, I mean, Scotland's running 35% now. They've got a goal of 100% by 2020. Okay, so are these crazy or what? You know, so again, I'm just trying to get, what is this number? You know, well, okay, so here's the Danish system. And if the world of computers works, I'll show you it in real time, but just to give you a key to it. So Western Denmark, Sealand here, the eastern island, which has Copenhagen. This is Sweden here. Norway is up there. And you can see the sort of high voltage system here connecting the country. There's several offshore wind farms. There's zillions of wind turbines on land they're not picturing. They have connections to Germany here and here, connection to Sweden there, connection to Sweden there, and then one to Norway, which goes up right about there. So notice this was a snapshot I took on Saturday, 2 days ago. Central generators, 1.9 gigawatts. There's about a 4 gigawatt load average. At the time I took this snapshot, it was 3.8 gigawatts. That's load, L4berg. And so we've got decentralized thermal plants, and then wind is 2.7 gigawatts. So it's substantially more than the central power plants. Net export, 1.2 gigawatts. Carbon production is 257 grams per kilowatt hour. So coal's about 1,000, natural gas about 500. This system is running at about half the carbon emissions of clean natural gas. So let's see how it's doing in real time here, if I can bring it up. Let's see. So this is right now, Denmark, and we're running at 3.2 gigawatts of wind, and the load is 3.5. So what's that? They're running about 85% wind power right now. So this looks like that 20% maximum might not be correct. They're exporting. There's a fair amount of export here, 2 gigawatts. And they're still running some of the central plants. They're not turning it off completely for system stability and other reasons.
Are they exporting to Germany?
Yeah, they're exporting so they got 2 ties. This one, they're exporting 200 megawatts, and here they're importing 300 megawatts because the needs for power in the country are different, and they're going by markets. They're not saying, we've got excess wind, so therefore we have to export through all channels. They're saying, what's the relative price here versus there, and do we import or export? What's the relative price here versus there? And similarly with the Scandinavian countries. So right now they're exporting to Norway 600 megawatts, to Sweden, that northern link to Sweden, 700, and then the southern link to Sweden at 800. So they're powering a lot of cities in Germany and Norway and Sweden right now.
So do they have storage combined here?
No storage. Nope. Well, I mean, sure, they've got storage. They've got Norway and Sweden, which is closing the locks on the hydro dams running off Danish wind, and then later or tomorrow they'll open them up.
So they're using hydro?
Essentially, yeah. But it's not conceptualized that way. It's you want to buy power? We got extra power. What's your price? Oh, well, sorry, we're going to sell to Germany right now. So it's a market trading of high voltage, from bulk power.
But they're not pumping any hydro?
Very little. No, Denmark has no pumped hydro. I mean, literally, Denmark has no storage. It's a very flat country, which is great if you're a bicyclist, but it's bad if you want to build pumped storage. They may have pumps. I don't know about their pumping capability versus just closing the sluices. I don't know. Yeah, maybe. I just don't know about that. Okay, so that's sort of real time, and it works. So I've actually been to the control center at Energinet DK. Let's see if we can get back to my PowerPoint here. Right. Okay, so oops, that is the running one, and I want to get back to this one. Yeah, so we're back to the static picture. Okay, so control center that runs this. It's right here. It's called Energinet DK. It's right under that power plant. And they are operating this system, and they're trading with the neighboring countries. So here's the shift operator at a point when they were running about 50% wind power. Running the whole country, 50% wind power. That's impossible according to the first slides you saw in this set. And actually, the shift operator does look a little worried. You can see he's got the same map that I just showed you, plus a more electrically oriented map. He's got a bunch of people who turn things on and off and make phone calls and so forth. Yes, sir?
They are a rather small country. What is their density of wind turbines per capita? It's obviously quite high.
I'm not sure density per capita. It's a 4 gigawatt load, and I forget the population. Somebody help me. Maybe 3 million or something people.
I think I once read 8 million.
Okay, that's more than I thought. Okay. So, yeah, it's a small country. They're transmission connected to other countries, so it's really a larger interconnect. Right. I mean, you saw from the transmission diagrams that electricity doesn't stop at the border. They're part of two larger systems, the Central European interconnect and the Nordic interconnect. Anyway, this is controlling all this. So, and these guys tell the national government that they can go to 50%. And when I get them off in a room and there's not any officials around, and I say, can you really do 50%? And they say, well, there's going to be some challenges, but we think we can do it. And there's a national commitment to it, so we're going to work very hard at that. So that's, you don't always hear that attitude. But the guy does look worried, and I asked him what was up. He had all his papers on the desk, and he sort of stopped for a minute to talk to us. So they had just lost a 500 megawatt coal generator, just tripped off unexpectedly. That was the big problem.
You don't take any agency for that?
I don't take any agency, no. It had happened before I came into the room. I probably caused him to not react to it as fast as he should have. But anyway, so, these things happen. But at the moment, the wind, 50% wind at that moment was not the problem. He had an unreliable thermal plant, but luckily he had highly reliable wind power to back up that coal. Okay, so what can we conclude from all this? We can integrate some amount from variable generation, and that amount is somewhere between 10 and 100%. So I didn't find in all these resources and travels and web searches and articles what I thought we needed. I believe that between 10 and 100% is not sufficiently precise. It may be it may be accurate, but it's not precise. Okay, so we need a scientifically defensible integration limit, and while we're at it, we'd like to make sure we understand how to do high penetration variable generation, because we don't really know how to do it. And we got one example that gets up to, that's around 30 or 40% on average and gets up to 80% sometimes. Is that the cheapest way to do it? So now I'm going to shift into reporting a particular study led by a PhD student who has now finished his PhD. This was a major part of it, Corey Budacek. And here we used hourly weather and hourly load. We're taking a sort of Pacala and Sokolow approach of don't wait for the new technologies. What have you got today? Or, you could say the Apollo 13 approach. If you've seen the movie, the vessel is, the space capsule is not working correctly. What do we do? What can they do? And in NASA on Earth, somebody came into the room with a box, and they dumped the box out on the table, and they said, this is all the stuff they've got in that capsule that can be used. You guys figure out how to use it. So that's sort of the problem. We're going to use today's variable generation, today's transmission, and so forth, and see if we can deal with this problem. And I'll credit Rob Sokolow for making me think that way. Okay, so, and we want to do an RTO-sized region, something bigger than Denmark, and we want to span wind regimes because, how many meteorologists in the room? Well, that's sad, okay. We want to be working at the synoptic scale, that is, the scale at which you go from one weather system to another. So PJM is the RTO we're going to use. This is what PJM looks like today. The time that we sampled it, it was not quite as expansionary as it is in this picture. It's cut off about there. But this gives you a sense of scope. You are there about, and it's a big system. So Denmark is 4 gigawatts average. PJM today is about 70, is it It's in here somewhere, 87 megawatts average. I said 70 before. Probably 2 years out of date there. We're actually going to look at a little bit earlier phase on PJM when they didn't have as much land because we had 4 years of records where it was all the same system. We're going to be looking at about 31 gigawatts of power and how can you meet, how much variable generation can you put into that and run it. This is an hourly model. We're just looking at the meteorology overall. We're not looking at transmission whatsoever. It is an incomplete model. It doesn't go down to the 5-minute level, but I think it gives us a sense of things without being combinatorially insanity. Warren Powell and Hugo, who's here right now, are working on, and colleagues are working on a much more detailed model, which we'll use to refine what I'm going to say today. Okay, so again, wind diversity. It's not, it blows. You saw that map of where the wind usually, overall for the year average, it's all in the Midwest, and we can see a fair amount here. These are stream lines, so longer and thicker streamlines indicate faster wind velocity, and the direction of the stream indicates the actual direction the wind's blowing in that location. So PJM covers this area, right? So we might have had a lot of wind farms out here at that time, which actually was yesterday. These would all be dead. But here, where it's not actually usually as windy, all the wind up there is blowing like crazy at the time of that snapshot. So if you remember the moving dots, I'll save one transition on the projector and remind you that we also have a large resource offshore. So now, what's our gear in the box that got dumped out on the table at NASA? Okay, wind and solar. They're commercial, they're large scale, there's insane amounts of resource. We can do it at near the cost of the commercial power, above probably, but near it. The next tool is transmission linking places with diverse wind regimes. This is really important. It's so much cheaper than storage. We're still going to need storage, but we want a transmission that connects diverse wind regimes that blow at different times. And so you want a lot of meteorology that goes into transmission planning. That is not the way transmission planners think about it right now. And we do want some electrical storage, and we want to put electricity in and get electricity back out. We're going to compare 3 types. Hydrogen, we're going to be inefficient and make the hydrogen by electrolysis because it's a simple electricity in, electricity out system. Is one. Central batteries, where you buy the batteries, you put them in a warehouse, you pay rent, and you have a guy maintain them and so forth. And then the third form of storage is grid-integrated vehicles, that is using electric vehicles when they're parked and not being used for driving, which is 23 hours a day. Use them for storage. And then we also want to do one-way storage, which is heat storage. If you have excess electricity, you may find that it's very cheap to store it as heat if you're at a location where that heat is going to be used later. Okay, so that's the toolkit. And how do we do this simulation? It's a simulation, of course. We didn't actually build the system, which would be very expensive. So the simulation, we calculate the cost, capital cost for the hardware. You're buying wind turbines or solar panels. And then we calculate the O&M cost, the operations and maintenance for running it. We take 2 costs. One is so-called current 2008. It's getting a bit out of date right now. So that's a bit high, much higher than today's prices, actually. And we also use future costs from published articles that gave estimates of capital and O&M costs in 2030. Obviously very speculative, but it's probably more accurate than using 2008 costs for something that's 20 years in the future. When we calculate the cost of fossil fuels, when we calculate the cost of fossil fuels, we add in what I call a cross-sector subsidy. Some people would call it externalities, but you got a big natural gas or coal generator, you run it, you produce electricity, somebody buys electricity from you, they write a big check for that electricity. And then also 50 people in the neighborhood get asthma, one time in the year, sometime over the time of the year, 3 people die that wouldn't have died. That's a subsidy that the health system pays you essentially by you avoiding that cost. So I'm calling that a cross-sector subsidy. An environmental economist would call it an externality, which is a word that you're almost guaranteed that no one but an economist will understand. So to me, cross-sector subsidy is more parallel to a government or taxpayer subsidy. That's really what we're talking about. So you can tell me it's a terrible term after if you want, but that's what I'm talking about. And then also, we're not, there's no renewable energy credits here. We want to really know what the true social cost is, so of course, we're not going to include production tax credit and all that stuff. So we're really trying to get the true social cost here. Okay, so another part of the method is that we use these 3 variable generation sources and vary them. Well, that's in the next slide. We assume perfect transmission, so we're not counting for a transmission cost. You could add maybe 20% to our costs if you want to be not so generous about that. Yeah. And then we try to look at 3 systems. It's incredibly computer intense to do this. You'll see why in a minute. So we only looked at running on wind 30% of hours, 90% of hours, and 99.9% of hours. If we'd had another few weeks of computer time, we would have done 100% because everybody says, why didn't you do 100%? But it may be asymptotic. I'm not sure it's really worth doing 100%. I want an 80% reduction, and 90% is pretty good, and 99% is great. So what do we do the rest of the time? We're going to use legacy fossil. Hey, there's tons of generation out there. We don't need to cut it off and shut it down. We do need to use a lot less of it. So that's what we get here, and I think we're going to get some pretty substantial cost savings by doing that rather than trying to cut it off. So the model is you take each of the resources and the storage system, divide it into 70 segments, and then you have a very big iterative loop that does 0, 1, 2, 3, up to 70 for all types of generation and storage. And what we pick, first we pick the combinations that'll run for 4 years without ever failing to meet load. Well, if there's, say there's 1,000 gigawatts of wind power inland in PJM, we divide 1,000 into 70, and so we do, well, let's say it's 700. So we're going to do 10, 20, 30, 40, a lot of iterations here. So what we're doing is building billions of electrical systems with all different combinations of inland wind, offshore wind, solar, and storage. Now, why would we ever do that? Because we didn't know where the minimum costs were. So we're building billions of electrical systems, running each one for 4 years, and the ones that actually keep the lights on, we say, how much did that system cost? So we're 70 increments of each resource. So, yes. Yeah, I mean, if I'd said 100, it would be more simple, but we'd still be processing computers, yeah. Equal amounts. So let's just say there's 70 gigawatts of wind. So we go 0 gigawatts, because each one could be 0, 1 gigawatt, 2 gigawatts, 3 gigawatts. And for that 1 gigawatt of wind, I now do 0 gigawatts of solar, 1 gigawatt of solar. Yeah, it gets to be a big number. So we tried out 28 billion electrical systems. This is why we didn't want to do a lot of processing on each one. We did do hourly for 4 years. Does it make load, is the question. Or does it make load at least 90% of the time, or at least 30% of the time? Okay, so what are the results? What we're going to look at is the 99%, because that's sort of interesting, because it's really pushing the boundaries. We're going to look at the relationship between load and these generation types. So this is load here is the black line. That's PJM load hovering around 40 gigawatts. These are hours in the bottom. It's sort of on a 4-year scale, so not very meaningful. But you can see the daily cycles of load. So this is 1 week. This is the most challenging week in the 4 years. And you can see we've got some pretty substantial times where we fail to meet load. And you can also see just kind of first quick blush here. There's more onshore wind built. It's the cheapest. Next most is offshore wind. That's this blue here. And then solar is coming in as the smallest. And this is a cost minimum. So that's why we have these fractions.
On the horizontal axis, those are hours?
Yes. So 24 hours is one trough to trough. 7 days across. So early in the week, we did not have so much offshore wind. Luckily, we had solar coming in almost at the trough there and there. But we just are very short. This would be very bad if there were no storage or anything else. The second half of the week, we're fine. You know, we had almost offshore wind alone was almost enough. There's one shortage there. But really, we have a lot of excess.
You're not showing the hydrogen storage,
No,
but
there's no storage yet. That's going to be the next slide. Yes. Yeah, because, right, that's misleading. I probably should strike that. The reason is because we get different amounts. If our storage is more expensive, then we get more offshore wind because it's more level. If our storage is cheap, we get more inland wind because it's the cheapest and we don't mind building more storage. It's like, it's picking the cheapest system at each level. Okay, so let's add storage to this now.
because right now you're using this heritage legacy fossil for
That you would have to, right, yeah. So when we add storage, now we just put all generation is green. In fact, it all is green. So all the generation is green, and then energy from storage is the gray, filling in. And we also use green for when the renewable energy is filling load, so it's being used productively. So green is renewable energy being used productively, and this kind of pukey orange, or pukey green or whatever it is wasted renewable generation.
One of your numbers is going up just by 70 increments is the storage line.
Yes, that's right. That's right. Yes. So just to give a sense, I mean, this is without storage, lots of gaps, big problem. Maybe you just burn old legacy fossil, maybe that's okay. And then fill it in with storage, and we get, you know, pretty much, we're always meeting load. In fact, there's this one time when we don't. We burn a little bit of fossil right there. And that was actually a power constraint rather than an energy constraint. The amount of power we could get out of storage was limited, and so we just filled in a little bit. And then this was the lowest cost, so that meant it was cheaper to do that than to wait all year and only use it once or twice. That's how this 28 billion electrical systems, I'm only going to show you the least cost ones. And it makes the talk a lot shorter. So that's the worst week in the summer. This is winter. We got tons of wind. We actually did need storage a little bit. But just for contrast, you know, the most weeks are not challenging like that one I showed you with big gaps. Exactly. So how can it be? Yeah, right. How can it be the most efficient? Because it's cheaper to, right. It's cheaper to do excess generation than storage. That's sort of a major unexpected finding from this, by a large margin. So if you look at this in terms of storage and so forth, it's terrible. I mean, you're actually storing, so you used a little bit of storage there, and when the week started, the storage wasn't quite full, but all that pukey green color, you're throwing away electricity. Yes, sir?
How did you decide on the architecture where the farms will be located?
Simple model, we just distributed them in the windier sites. which were already known. We had meteorological stations. We just distributed them out. We didn't choose one place versus another. If we could do that, we would have actually done better. So we had spread out through the land sites and spread out through the ocean sites, and the rooftop solar, we just had also spread out for the building side. Okay, so we know we had enough resource. How about reliability? We found that at all three of these levels, we actually can run the electrical system. We can even run the electrical system 99.9% of the time from all variable generation and storage, but per Rob's question, is it going to be too expensive? So we got to return to that question. But we can check off reliability. It's possible, but at what cost? So we can calculate the cost for this. We know the capital cost. We know the O&M cost. So what does that look like at 2008 prices, which is a bit more than what you would pay today? Well, actually, surprisingly, you can run 30% of hours totally on variable generation and get 51% of your energy, and it's about the same cost as today, depending on how you want to measure today's cost. I would say 8 cents per kilowatt hour in PJM when you consider that it's mostly bilateral contracts, which are load following, and we are providing load following power here, not bulk generation. So 8 cents, but it's 9 cents of externalities. You know, you can debate the externalities, so I break it up here. You can just take 8 if you want, or you can take 8 plus 9 if you believe me on the externalities. I would say this electricity is 17 cents a kilowatt hour when you include cross-sector subsidies, and I'm not going to include subsidies for renewables, so it's a fair comparison, I would argue, yeah.
So is that 11 cents inclusive of distribution?
I cheated and didn't calculate the distribution costs. Add 20% to that if you want to have I think, a fairly pessimistic addition. 20% of the cost of the electric system?
So it depends on in New York City.
Okay, that's, yeah. New York, this is not New York City.
Here is, I think, my bill's 15 cents per kilowatt hour.
Okay, that's mostly distribution.
Yeah.
Yeah, so the distribution doesn't change. All we need to do is upgrade the high voltage system. Well, it's not, busbar would be at the plant. We need to get to the substation. Yeah. So we didn't include that here, and I'm just kind of warning you if you want to be more careful. I mean, I wish I could have modeled transmission. Hugo and Warren are going to do that. We're going to have some actual data. You know, we'll see if it blows these numbers out of the water or what. But this does not include transmission. My guidance is add 20% for that. You don't have to believe me.
What about the cost of the existing traditional plant for depreciation? You still have to pay that fee for these.
Well, that's a policy debate that would be fun to have. Yeah. Were those imprudent decisions by people who bought large fossil generators at a time that, you know, carbon reductions were coming? Is this something that doesn't get built for 30 years and it doesn't matter anyway because they're all totally depreciated? I'm not. Yeah, I'm not. Yeah, right. Yeah. I'm just asking, does the weather let you do this? I mean, really, this is mostly about meteorological variation and how it affects the weather system. But, you know, I'd love to have debates about things like who picks up the tab for that big, old, dirty coal plant that one of my friends just bought. Okay, so, you know, what's the cost? Well, it's not bad for even 50% of energy, but if you want to go up to these high levels, man, you're going to pay for it. 28 cents a kilowatt hour, you know, even if you take the total, you know, cross-sector subsidies, externalities, whatever you want to call them, it's still only 17 cents. So you can't tell me, hey, I'm going to do it for environmental reasons, I still want 90%, because the environmental reasons are factored into this comparative number, this 17 cents. So this is expensive. Now, you know, I'm grateful if we get 51% of the electricity decarbonized, but of course, I haven't gotten to the 2030 numbers yet. So conclusions from the 2008 costs, the kind of today's cost plus a bit, cost effective for up to 51% of energy, and that model primarily builds, that cost minimization model primarily builds inland wind. It does not build much solar, it doesn't build any solar actually, and it doesn't build much offshore wind. And it gets expensive for more. Okay, so 50% yay, 90% nay. Okay, but costs, these are all dynamic costs. They're moving fast. I'm worried, a little bit worried about time. How am I doing? It's 5:30, it looks like. Stop soon. Okay, sir.
A question regarding the externalities. Did the 9-cent addition include just the immediate cost benefits of air quality, or did it also include the cost related to the long-term causes which you identified, like ocean acidification or climate change?
I think it was an underestimate on those latter ones. We used all this is from published estimates, so we didn't pick our numbers. We just got consensus studies. Oops, did I finish that? Yeah, so what's the mix? What's the mix that you get? And I don't really have time to go through this in detail, but I will recommend the paper version. I've got a couple of copies with me, and I'll give you the web reference. But, running with, and this is actually 2030 costs, but when you're running low, 50% of energy, when you're running low amounts of renewable energy, you just build the cheapest stuff. If you want to get to these high levels, you really need that diversity, so you're willing to pay for more expensive generation, in this model, rooftop solar and offshore wind, because it's more evenly distributed in the case of offshore wind, and it's load peaking in the case of solar. It's midday. So you spend more on the expense of renewable generation so that you don't need to spend as much on storage. And when you get even to these very high numbers, because you have all this excess generation, the amount of storage you need actually goes down again. So we've got a big ramp up in storage to get from 50% to 90%, but then it starts dropping as we build more and more generation. Again, these are the least cost models. It doesn't mean it's less cost than today. It's not. But the least cost is to do more diversity of generation and less storage. We're still building a lot of storage, don't worry. And the energy numbers are there. I'm sorry, I can't go through all that. So what does it look like at 2030? What we see, and you've seen in some of these slides already, we're doing a lot of overgeneration, maybe 2 to 3 times as much. And less storage. This is all these bullets are things I already said. So let's look at 4 years just for fun for a minute. I mean, it's crazy. This is load. This is offshore wind, and this is inland wind. So to get 99% most cheaply, if you're willing to pay for 99%, you do this large amount of overgeneration. Another sort of 4-year snapshot is generation amount in storage. So this is megawatts, and that's megawatt hours. And then how much you burn thermal, your legacy fossil. It's kind of surprising. 4 years, we turned on the old generators 5 times. We ran the whole system. But you can see what's happening to the storage. Middle of the summer, less wind, more load. You're drawing down your storage, and then you hit the bottom, and you got to turn on your legacy fossil. But it's not that many times, and it's not like you don't have to worry about it in the winter. You could drop a bunch of stuff offline in the winter, it wouldn't matter. But you really have to keep your stuff running midsummer. And it's a few episodic events, too, so if you can do some planning, you can minimize that. Okay, so now 2030 costs, it's roughly half capital costs, roughly the same O&M costs, just so you can think about it. It's not so bad. It actually turns out about the same for the 30% case, because we weren't using that much storage then anyway. The 90 and 99%, we've got less cost for our variable generation, so the cost optimum builds more variable generation and more diversity of it. Therefore, you need less storage. You really get a pretty substantial drop in price. And again, I think the comparison number is 17 cents per kilowatt hour. If you want to compare it with 8, that's okay. But that looks like 90% is either a lot cheaper than what we're paying today, including the cross-sector subsidies, or it's about the same as what we're paying today if you just look at the energy coming off the transmission lines. 99%, again, gets a good bit more expensive. And a lot of those graphs were 99% when you had all that excess generation. But still, hey, coincidentally, it's actually arguably the same that we're paying today. we had the same reaction that Rob did. Man, we're wasting all this energy. And of course, if we talk to any commercial wind operator, they're going to say, Kempton, you're being a lunatic again. We don't want to build these wind farms and not get paid for them. We're not going to do all this excess generation. I said, but the wind generators are a little cheaper and all that stuff. So we said, well, what else is going on at the time we've got all this excess electricity? We're not going to build an electroplater on every block. So what else are we already doing? So we said, well, how about building heat? We got a lot more in the winter. So let's look at natural gas use in the commercial and residential sectors, which is a rough gauge of low-grade heat needs, and compare that with the excess wind. This is one of those graphs you say, wait a minute, guys, you took the same column out of the spreadsheet and plotted it twice. So the residential commercial natural gas consumption is almost exactly the same as the excess electricity. So, of course, this wasn't in the big model. We just did a stupid monthly thing and said, let's just sell it at the cost of natural gas, really cheap electricity to use for heating. I don't know how you work that out commercially, but if you credit the cost of natural gas, then the costs come down even more. And of course, by the way, you also eliminated all that natural gas consumption. So 3 criteria. If you're looking at 2030 costs, not 2008 costs, we've checked all the boxes here. And I'm now going to do my last slide, which is findings. So as far as we can tell, you can integrate as much variable generation as you want. But don't think you're going to be producing 100% of power. You're not going to be producing 100%. You're going to be producing 200% or 300%. And maybe that's bad or maybe it's okay. But yes, we believe that you can integrate a lot. And remember, we took the hard case. No hydro. We disconnected PJM from all its neighboring RTOs. And we only used 3 sources of generation. Nothing which had inherent storage. So you use transmission, use synoptic scale weather patterns and understand that, and use diverse generation sources. After all those, you use storage. And by the way, the cheapest form of storage was using electric vehicles because somebody else already bought the batteries. That's another story. And we use most of the excess electricity for heating, which is pretty much using up all the excess electricity. Cost parity you can get at 2030 capital costs. That's the story. I'm sticking to it. Reference. Thank you.
About 5 years ago, I heard a talk given by someone from NIST, I don't remember who it was, did a similar study, and he concluded that the most amount of variable generation you could include would be about 35% if you wanted the same reliability and cost. What do you say to that?
I bet he only looked at one electrical system, and we looked at 28 billion electrical systems. So, I mean, yeah, you saw I cited studies that had those kind of numbers. The conventional wisdom, even from the American Wind Energy Association, is less than that, 20%. So there's a lot out there, but when we try to dig into them, they either are just myth and, fear, uncertainty, and doubt, or they're studies that only have a very limited approach, in my view.
So in what you did, the analysis assumes perfect transmission. And
yes.
So what would change if you started to think about the complexities of the transmission issue, the transmission and distribution issue?
We wouldn't have enough computers.
Well, aside from that,
okay.
Suppose you did. Can you
well,
speculate?
I just gave a really crude sort of ballpark number of add 20% to the cost, but I don't really know that. I'm working with Hugo, Warren, operations research folks. We're going to have an answer to that. Partial answer. It's not quite the same parameter setup and all, but we can answer that better in a year or so.
I mean, just to follow up for a second, I mean, so you considered different, I'm thinking of your Apollo 13 box of things. You can also do the same exercise for transmission.
Yes.
Right? So is that what Warren is doing? Or Hugo? I don't know.
Yep.
Not exactly the same approach as Willett was describing, but we actually are modeling the transmission into the simulation and limited, unlimited. And what we are doing also, that Willett hinted at, but is bringing it down to the 5-minute level. And that's where there is a question, an issue, which we are dealing with. Initial results have shown that at the level of the 5 minutes, we may have some lack, some need there, which we'll have to think on how to supply. Because at the hourly level, even in our preliminary results, we don't see any shortage. So in that sense, we confirm the GE study of a few weeks ago. But when we come down to the 5-minute level, that's where there are issues there, and we want to check those and come with them.
One more question, and then Dr. Kempton.
I don't think it's right now. This model is for the 7-state area that you were referring to earlier, plus DC?
Yes. Is it 7? I don't remember exactly. It's traditional. It's 2002 PJM.
Thank you very much.
Thank you.